So, Uriel, you start.
Okay, yeah. So maybe a year ago or so, I started speaking to various people, including where is Eric? He's gone. Okay. About the interest of
our fourth panelist just arrived.
Of having at some point a meeting, I would rather say an international conference, where people who are actually doing somewhat similar things but in totally different fields will have a chance of talking to each other. For example, those people who do reconstruction in genetics, who look at Basques, Jews, whatnot, and then try to find where they came from. People who look at, some of them being ladies, look at present-day galaxies, not present-day Jews, and try to find where they were 14 billion years ago. And there are actually quite a number of other things. I mean, in linguistics, it's not just problems of reconstructing dead languages. Can you close the door, because there's a lot of, or unless you are able to convince people to stop talking,
No.
Just close the door. Yeah. Now,
it's okay.
If one, you know, there is in science, at least in some science, there is a defined thing called mathematics, and if one tries to look at reconstruction from a mathematical point of view, it differs drastically from what we generally call the Cauchy problem. A Cauchy problem is an initial value problem. You prepare a system, you set the state, and hopefully you know the equations. They may be non-trivial to solve, and then you want to find what is happening to the system later, either in a deterministic or in a statistical sense. These are the initial value problems in mathematicians call the Cauchy problems. Reconstruction problems are sometimes viewed as just backpedaling in time, but that isn't quite correct. For example, the problem that Roya, the Persian princess who sits there, talked about, if it were truly a backpedaling Cauchy problem, then she would have said, she didn't, that we now know the position of the galaxies, and of course we know their velocities, and therefore we start backpedaling. Of course it didn't say that. The only thing that we know is where they are now, how they are distributed in space, not just statistically, but where exactly they are. And we also know that decoupling, or whatever you want to call it, roughly 14 billion years ago, the distribution of matter in the universe was essentially uniform, with very tiny fluctuations. And then you actually have a two-point boundary value problem. You have a condition there, which is now, a condition here, which is a long time ago. And then, if you're lucky enough and they're able to find a variational formulation of your problem, and now let me be mathematically pedantic, if there is some action functional and it happens to have suitable convexity properties, then if you're really very lucky, then you can prove that there is a single minimum and a unique reconstruction. There are such theorems. Now, it is, pardon me?
And if you're not lucky, what do you do then?
Yeah, yeah. I suppose that most reconstruction in other areas, like in genetics and also in linguistics, must be using at least implicitly assumptions about what was happening in the distant past, and maybe by trying to make better use of what we know, even if it's statistical information, they will be able at some point to do a better job in reconstruction. The non-trivial question that was raised by Jim Peebles. Jim Peebles is you know, after the talk of yesterday, we are all polytheists. So Jim Peebles is one of the gods of cosmology.
Donc pas pétroleur. Donc pas pétroleur.
Yeah, okay. Whether you
gods must have unbelievers.
Pantheon,
Gods must have unbelievers.
Yes.
yeah. So Jim Peebles, who's a friend of mine, I discussed this with him just about a year ago, and he said that this would be very interesting, and people could have great fun learning from the other fields and so on. What still remains to be seen is whether one can expect a significant amount of cross-fertilization. So, and then this matter was discussed in more detail with Eric Orel and others in February, I believe, this year. And we thought that maybe the best way to get some idea of what can and cannot be done is to begin by having such an event on a much smaller scale. I think we tentatively called it the kindergarten, where you would have a bunch of biologists or cryptobiologists with maybe a physicist past, lecturing to a bunch of astrophysicists and other during 3 or 4 days to give them the first idea of what one does and so on. See, we haven't taken any steps yet.
We are doing it now, Uriel. That's why we have this round table.
Yes.
Yeah. Should we get some reels? I mean, this is getting a bit. Ooh,
yeah.
This is getting
No,
I want some more action, okay?
Yeah,
so, Goya, could you please stand up and now tell what are the problems we need to solve in reconstruction for you? You told me that you would do that, okay? Come on.
They have to stand up?
Yeah, that's better, yeah.
Well, part of the problems I talked about yesterday.
Yeah?
So, basically the reconstruction we've done worked on certain scales, and you saw that when we compared it with the simulations, there were areas where the reconstruction didn't work. And so part of that is because our hypothesis, the hypothesis of convexity and potential flow. So what's needed, and actually that's part of that we discussed with Uriel, is to improve on that. So see, if you just relax these two hypotheses, what can you do? I think that's the major things, step that could be done. So it's also related to the fact that what we're assuming is that these particles for which we are finding the Lagrangian positions doing the construction, we are basically moving on straight lines in an expanding universe, right? One shouldn't forget that. It's not straight line, it's very different from a straight line in a non-expanding universe because there is gravity. So first step would be really to do construction, not assuming this straight line motion. And Uriel can say more on that. I think there was some, theoretically, there was some formal progress made by Bernier and his student, but we never managed because the student left actually to go to finance, so he's making a box of money.
Is he reconstructing?
He used to make works.
Some people make a lot of money.
I think it still is probably because he's not coming back to his position, which is still open for him. So we have basically made no progress there. So basically one question, immediate question, would be to do reconstruction on small scale. That's one thing. And for the time being, we have no real practical recipe for that.
Yeah. Right. So Timo, I mean, I'm not sure everybody realized this in the experimental part of Timo's talk yesterday, but Timo showed very honestly that reconstruction was not perfect. You had this experimental thing with people copying each other's texts, and there was a known tree, and the reconstructed tree was not the same as the known tree. You didn't comment, and nobody asked the question.
No, that was clear.
Okay, that was clear. Yes, okay, I'm just reading. So maybe you also like to comment. What can be done better for reconstruction? Ideally, you would like to reconstruct these trees. Yeah? You have the data. There's no doubt of it, of the data, your experimental data.
You also have to stand up or not?
Yeah, especially. Yeah.
But then we'll sit down.
Yeah.
Yes, well, in a way, it's, I probably didn't emphasize it enough because I kind of felt that it's obvious, but that's usually a mistake and assume something like that. But the thing about this is that it's obviously a statistical problem in a way. We don't know the laws of making mistakes. We just have some regularities or statistical ideas of how people would make mistakes and how people would copy texts. And given that the length of the texts is sometimes modest, and sometimes you only have partial knowledge of the text. Some of the text might be lost. We deleted on purpose some parts of the text and stuff like that. So we kind of introduce noise in the system or in the observation system. And then it's obvious that you cannot really get a perfect reconstruction. So in that sense, it is clearly a statistical problem of inference and not a mathematical problem of inverse. You cannot just solve something and expect it to be the real thing.
Yeah, there is actually, I see, a rather drastic difference between the reconstruction that we do in cosmology and that the one that you talked about, namely, in cosmology, we start with a state of total disorder, where if you, except for a almost uniform background, the fluctuation on top of that are completely random, they're Gaussian. There's no structure whatsoever there. And we wait 14 billion years, and it's full of structure, actually a very beautiful structure sometimes.
Forgive the very naive question, but isn't
and
this like...
you have the very opposite. You start with, hypothetically, a very coherent text,
That's
and then through that copies, it gets Gaussianified.
Yeah, sure. I think that's a very common principle for textual criticism, that you prefer the more structured or non-trivial version of the
But
text.
there is, let me go, I mean, from give an argument in the opposite direction of what I just stated, and which merges partially with what Roya said in small scales. Cosmology on large scale is a bit boring, because on large scale the universe isn't old at all. Most people here do turbulence, and we have a concept of eddy turnover time. And as you know, that is very much scale dependent, and typically the larger the scale, the longer the eddy turnover time. It's the characteristic time for nonlinear processes. In cosmology, when we are on sufficiently large scales of tens of hundreds of megaparsecs, the characteristic time becomes longer than the age of the universe. And therefore, things are much easier than in turbulence. In turbulence, if you stir your cup of tea or coffee, very quickly you have tens and hundreds of any turnover time that have passed. Not so up there. But on smaller scales, on scales where all these multi-streaming effects are strong, etc., there the dynamics is very different, and it's beginning to become perhaps not turbulent exactly in the sense that we understand in compressible hydrodynamics, but information gets lost, and in an irreversible way. There are certain things that could certainly not, I mean, definitely not be reconstructed deterministically. Because of all the phenomena of chaos that appear there, but they're only on small scale. Of course, what we call small scales in cosmology are not millimeters. Yeah. There's more like from 1/10 of a megaparsec to 1 megaparsec or so.
But so in Teemo's data, if I remember correctly, the small scale structure of the trees were better reconstructed than the large scale. Often one could see a small subset of the tree which was perfectly reconstructed, but the whole tree was a bit off. So this leads me to the question which I have to ask to Roberto, because you've been so totally silent. Are there similarities or analogies between different reconstruction problems?
So, assuming that I'm not the god of this answer.
Of course you are. Temporarily.
First of all, let me tell you that I should add few other items on this issue.
Okay, tell me, which ones?
At least climate,
Yeah.
which is almost a professional work. People make reconstruction of past climate since 50 or more years.
Yeah.
And then, according to the way in which we define reconstruction, again related to climate, it's data assimilation in modern meteorology.
Yeah.
Okay? In other words, what people usually do now is to take observation day by day, and then to start the forecast, what they do, they start in the past and try to guess what is the best starting point in the past to obtain the closest prediction of today weather. And from there, they can make the forecast. So the reconstruction of the today weather is one of the things that is operationally done. And it's a variational problem. Unfortunately, it's a linear problem so far. And you have all the troubles.
So far, but I mean...
You mean linear or non-linear?
It's only because it's done by perturbation.
No, it's only because it's done operationally.
Okay, same thing, yeah.
So, but in principle, it should be non-linear. The other thing which I should add on this list is, maybe it's there, but I don't know if it's there, is the social aspect of reconstruction. There is a lot of people working in trying to reconstructing the habits or behavior within the social in the society, even criminal behavior and so on, which again is a problem where you want to know where something is started, for what reason, knowing events that have been recorded during some period of time.
So history, but sort of...
History, yeah, but it's a rather operational one, okay? Now,
In crime history, what do you mean by operational history? What do you mean by operational history?
It means that you want to get to cast, for instance, you want to understand where and how is controlling the traffic of some illegal drug or something like that, okay? So this is done operationally. Now, other similarities or analogies? Well, I mean, this is a very difficult question, of course. In some cases, you can think of it. For instance, if I think of weather forecast, data simulation, and the problem that Uriel was speaking about in the universe, there are some similarities, okay? If I think about genes, whatever you think of it, and language, networks probably, there are similarities. But if I try to see some links between problems that you have in biology and problems that you have in climate, the similarities is the problem is not the way in which you make reconstruction, is the fact that some people works in climate looking at the biology of 2 million years ago. So there is no real similarity. On the other hand, some of these questions about network, language, and so on, and some of the problems that you can find in what I call the social aspect are very close. I mean, you can use similar algorithms, you can use a quite vast amount of, let me call it vaguely, neural network to make reconstruction. Once you can tune it on a given set of golden rules. Okay, but there are some similarities, but I would say that there are class of similarities. I mean, you cannot find really some common trends in all these fields. This is my feeling. Now, the first question is fragile. What do you mean, fragile problems?
Well, if there are similarities, you have. I'm not the answer. You are the panelist.
Yeah, but
I'm
I
just
don't understand the question.
Is it very sensitive to the data?
Okay. Yeah, there can be fragile problem and very unconstrained problem, I'm sure. There are both discrete and topological, and all these effects are there, according to my own experience. And, well, that's it. I mean,
So this is challenge Uriel. What you're saying basically is that everything except the universe is more or less the same.
No,
But the
it's the
universe
other way
reconstruction is different.
No, I say
That's
that
what
the
you said.
universe, the weather sometimes,
The way that the universe.
okay, you can put some class of problems within some box, and another class in another box. But not necessarily all of these problems are connected within the methods.
Yeah,
And,
sure.
well, I'm sort of listening, and we still didn't quite define what we mean by reconstruction. So let's try to do that. Are we meaning a situation where we have a limited amount of information, and we want to use this limited amount of information in order to gain fuller amount of information, or all the information that we needed to know on the basis of a limited amount of information? Is this the problem?
I would say that this is an
That's one
inference
of
problem.
that's one
That's
of
an
the-
inference problem.
Okay,
Now, that was-
Historically.
why don't you let me finish this?
Oh, I'm sorry. I thought
If the answer is partially yes, let me remind you of one case where we know that this has worked tremendously well. And that is in the context of the Duncan system theory with the Tuckin's theorem of reconstruction. That is to say, let me remind those who don't know probably everybody knows, if you have a dynamical system that has n dynamical variables that are coupled, but you don't have the information for all of them, you have only one, say a variable x, then you use the time-delayed coordinates in order to reconstruct the whole phase. This is a very, very clever thing that was extremely useful at the time, still useful for people who are doing this. So this is an example where you realize that limited amount of information hides the full information if you know how to extract the dependencies. That is to say, the idea is that if you have x at t and x at t plus tau, x at t plus tau doesn't depend only on x of t, but also on y of t, z of t, etc. So if you have enough such time-delayed coordinates, then you are done. So we know examples where this works perfectly well. The question is whether you shouldn't think along these lines also in other cases. As I say, if you have a limited amount of information, what are the causal dependencies in these limited amount of information? They can dig out from that limited amount of information to make you a more complete thing. This seems to me like a potential strategy that might work. I don't know how to do it in every case here, but No, maybe one has to think in such terms.
You want to say something?
Yeah, we have to be careful with that. Of course, the word reconstruction is not one that has been coined recently, and it can have all kinds of meanings.
That's why I'm asking the question, what do you mean?
And for example, the embedding of projected dynamics into is a rather well-defined and beautiful mathematical theory. It doesn't strike me that it belongs to the same category as those that we
That's
we
already
talked
been
about.
solved.
Hmm?
Already
Yeah,
been solved.
sure. But still, I'll try to comment on the very beginning what you said was the limited information. If one looks at how reconstruction started in cosmology in 1989, I believe, at least in a paper of Jim Peoples in 1989, at that time, one had much less information about the distribution of galaxies than one has now. In particular, one had a reasonably good information about well, our galaxy and its neighborhood called the local group. People's idea was to try, starting from the known position of some rather small number of galaxies of the local group, to see if he could reconstruct their dynamical history back in time, and from that infer what their velocities should be, because there were a few instances where their velocity was measured independently. And in doing that, he discovered, on the one hand, that the reconstruction, the way he was trying to do it was not unique. It was a big non-uniqueness problem that disappears, fortunately, when you go to the continuous limit and you have convexity, things, and reconstruction mathematically becomes a unique problem. For discrete bodies, it is not. But there is another thing at a much more cosmological level, is that there was an unknown parameter in the equation, which roughly you would say was the age of the universe, and Hubble constant, and things like that. And Jim Peoples found that with the value that was still assumed at that time, which where the universe was significantly older than it is considered now, his reconstruction produced velocities that were not consistent with the observed one, and that was one of the reasons which led him to propose a younger universe. So here you had limited information, just a bunch of galaxies, and the output was the universe must be significantly younger, which is not a negligible discovery. Of course, there were other signals coming from other observation in cosmology which were also pointing in this direction. That just was one of them. Now, from the point of view of the mathematical theory that we developed with Brognier and others, what people did was could be easily called total nonsense. It could be, but of course I'm not going to do that. Because non-uniqueness, not enough data, but still, there was interesting output of this. Because at all the error bars, it was still a very interesting output. So you can see that even with a rather modest data and modest goal, you achieve something. So one shouldn't, from a point of view, for a physicist, one should be aware that there are such things to be found.
Okay, so my answer to it, Tamara, is that reconstruction, to distinguish it from general inference task, is that you have a notion of time and you have the data today and you want to reconstruct the past. This can be real time, historical time, or some process time. Something is happening.
Third
And
one.
now, to answer you, Roberto, I think that all of these cases which you added together, networks, language, genes, books, and so on, and social aspects, generally we do know the data today, better and better. And we want to reconstruct the past that we don't know. The success that you, Ariel, are pointing to is a case where we know both today and some data in the past. We knew that the universe was always homogeneous in the past. And also for weather reconstruction, we know
People
that.
use that.
Yeah, people use that, and you use that, and that's maybe one reason why you're so successful. So
Yes,
really,
finance.
maybe these are two different problems.
Well,
Now, Roberto.
There's financing required.
Finance, yeah, okay, we can add finance. I'm not sure what should do.
You have all codes, right?
Yeah.
120
Yeah,
million.
to do what? Yeah, Roberto, what?
No, just,
So there you go,
just
predictions.
a comment.
Yeah.
I mean, there is an assumption that you know also, if you wish, that you think that there are well-defined rules to explain what you are observing.
It's not a random, it's not a random set.
Huh?
It's not a random set of data, right? Because
But,
then
I mean, it's not a random set, but can be easily be contaminated by random effect. This is certainly the case for climate and for weather, where your reconstruction is taken under the assumption that this is what you get with the law that you know. But of course you have to take into account that there are random effects, all the kind of, there may be some unknown features that you may discover in the future. Going to the universe, I want to ask you a question. What about the dark matter?
Well, I mean, technically, let me, I think I prefer that Roy answers this dark question.
So you mean, what do you mean?
I mean,
This
you
is
do the reconstruction,
It is on dark.
and then you should take into account also the dark
Of course,
matter.
but this exactly reconstruction is, galaxies are just like tracing dark.
Okay.
So because the whole theory is valid for dark matter, which is collisionless, has no dissipation, so you can trace it down. Now what's worrying me with those things is that when you look at universe, it's basically governed, it's deterministic, right? Because you have gravity, large, it's a long-range force. But that with other things, like books, genes, biology, finance, climate, it's sort of a statistical system.
Climate is also that.
I mean,
High dimensional.
This is part of your point about
Yeah.
defining, philosophers sit around in a room and talk about the state of brickness without defining what a brick is. And they go on, that keeps them employed for, whole careers. And it really does make a distinction between the knowledge that at least there's an underlying dynamical system producing this stuff, whether it's weather or climate. In the case of weather, in principle that you could do assimilation means there's an equation of motion that you're correcting all the time. You could do this in principle with the example you're talking about. With climate, there's a high-dimensional system producing your one-dimensional time series, which you can embed, and now you can produce an equation. Now, if you did the same thing and you looked at text and you just simply said at each iteration that's time, and you did embedding, what equation would you get? What's the underlying equation of motion? So isn't that the distinction that you want? Because you're putting physics into your thinking about it, and you're not. Right?
Yeah, but there are intermediate cases. Take linguistics. In linguistics, some of the evolution seems quite similar to the one you talked about yesterday, random changes. But there are almost deterministic mutation laws for consonantic mutation, etc., for which one can almost write equations. So it's a mixture of the two.
Well, this I've discussed with my linguist friends who have actually done a linguistic or language reconstruction, and that seems to be the kind of the strongest difference between what the methods that I'm using, where we assume that the changes are essentially random, and which is the same as the phylogenetic methods are using that for studying species or genes. But in language, I suppose the assumption is that the language change or evolution is deterministic. The rules just depend on at which point of the process you are. So that was kind of funny when they told me this, because I remember when I was something like 7 or 8 years old, and I wanted to learn how to read English text. The Finnish, I of course couldn't. And I was trying to learn it by comparing sentence by sentence, or word by word, Finnish to English, and trying to come up with a rule by which you could transform individual letters to something else, or something like that. And I couldn't. And later I sort of was relieved when I heard that this is not the way you translate, or this is not the way you learn language. And with this background, I was very surprised when a few years back my linguist friends told me that that's actually how it works. That's how, if you go back enough in time, there is a proto-language, and then they are claiming, which is something I don't completely buy, but this is what the fundamental assumption is that you apply a sequence of deterministic changes from this proto-language to create English, and on the other hand, to Finnish in the other branches of the tree. And then if you just put two sets of deterministic changes together, that should be still, well, basically invertible in case the changes are suitable. But I think that there is enough randomness there that is essentially it is not deterministic. It's just the kind of change that we also have in text. There are some regular features, but there's also randomness, and especially when it accumulates over a number of iterations, it becomes just a statistical phenomenon as any other. But still, the methods they are using and the fundamental assumption is that it is deterministic, except for some small deviations. But the methods are very different because of this.
But I mean, the distinction John made, are there equations, or are they just certain laws for how the random changes occur, which is not exactly equation? I mean, they may be rather for Planck equation, but okay. That makes a big difference. And it's not clear that that we can learn much from one type of. I mean, there are these extreme cases, purely random and purely deterministic, but we have all kinds of stuff in between there.
But let's take even the purely deterministic ones. Like, let's take even the purely deterministic ones.
Yeah.
Even those, when you want to go backwards, you have the problem of chaos, right? Any mistake,
No.
why not?
Not necessarily.
Why not?
No, we don't have that because we don't have the growth of errors. So on large scale, there is no such thing.
Why?
Well, in her,
It's potential flow.
Because
It's potential
well,
flow.
if I only backward
in
in time
potential flow, there's no.
with a climatic with a weather equation, I have chaos.
I mean, if you
Yeah,
want
but
to have
then
that,
the
you have to
flow
have a highly
has to be
nonlinear system, right? In order to, but this is not on large scale. The reason why it works so well is just this sort of more or less linear or semi-linear. So you don't have this.
So for linear problems, that can work.
Yeah.
But if it's non-linear, forget it,
No, it's
right?
not a question of being non-linear. For example, for the Berger's equation, it will be one-dimensional or multi-dimensional. You don't have any chaos, and you can integrate back in time as easily as you can integrate forward. Of course, once things are in a shock, then that information is lost. You may be able to find the interval that fell into a shock with what was happening precisely inside there. That's lost, but that's not by a chaos mechanism.
Yeah, but that's already some indication of how to separate problems, right? So then you know which ones are hopeless and which ones are hopeful, right? So say if you have indeed a flow, like potential flow or a linear kind of system, then you're in good shape. Otherwise,
But my question is, if it's completely random, right?
completely
But it's just like, gene and evolution of cells and so on, biology, complex system.
Well, we don't know.
So if you have got a present status, present distribution of something, and you want to know what the initial condition was, is there a reconstruction that we could do? Basically,
Yeah.
you would find
That's
initial condition,
Timo.
so you would find initial condition that statistically would evolve to the present state, or
Well,
would
I-
it be exactly?
I think what helps us in some of these cases, I think this is also a feature way that we can use to separate these things in two sets. Is one where we only have one system evolving, or one sequence to observe. And then we need to know the dynamics in order to infer anything about the origins when you know the current state. But then there's this other type of phenomena where you have branching, and then you observe not only one sequence, but you observe a number of sequences. And then once you've observed, I showed, well, the birthday example was just one example where you observe three final states, three genomes or three sentences. And from those you can infer something about the origin. But of course, observing just one sentence, it's impossible to say anything about how this sentence evolved. But so that's one difference in some of these things. For the universe, there's only one, I suppose. At least one of which we can observe any evidence. But for the texts, we have several, for genes, several, species, several, and languages.
But coming back to text, make an observation, well, it's a speculation which we destroy easily, perhaps. The text that we are trying to reconstruct, let's assume, just for a moment, that they are not particularly deep pieces of literature. That normal writing. Then we have various Markov chains that tell us that if a certain word appears, that the next or preceding word has a much higher probability of being this one than that one, etc. Okay. So these constraints play, to some extent, the role of our knowledge that the universe was uniform initially, because we now have a somewhat noisy text and we want to go back, and we have these probabilistic constraints. Somebody mentioned to me after your talk, was it yourself or somebody else in the discussion, that if one has a misconception about what these Markov chains are, and is thinking that the text is unsophisticated, whereas it's produced by a person of great literature and culture, then one can do it very wrong, because such people do not use the standard transition. They use more sophisticated ones. Okay, so things can become vicious. But leaving that aside, I mean, we are not necessarily trying to reconstruct Nobel literature. By the
Why
way,
reconstruct? The Nobel literature is printed. You cannot give the Nobel Prize to anybody who is not alive.
Yeah, but
with a few exceptions.
reconstructibility, by the way, I have here a conjecture,
Yeah?
that the reconstructibility, how should I express that? That the reconstructibility is correlated with the automatic translatability. I will say something nasty about Mr. Tranströmer, who just got the Nobel Prize in literature. Actually, I happen to like him. And he has been translated into many languages, 60 I believe.
Yeah, something like that.
And I tried the Google Translates on him, automatic translates, and cheap ones, because you don't have to pay for Google Translate. And on many of the short poems, did perfect job.
Is that true?
Yes, I can demonstrate that.
Master building, so it's not so deep.
That's how.
Yeah, exactly. Let me launch another. I guess this is the final team.
Not
discussion.
modern poets.
Okay. Yeah, modern poetry. Try it in Pushkin. Yes, of course. Yeah.
There's no meaning.
So Timo, our linguist friend in Helsinki, he indeed believes that languages evolve according to rules. You have a consonant change and so on. So whatever, for his case, it's the Uralic languages. Now, there are also these models which work on more final time scale. How do actually language change from one speaker to the next one? Because there are small random changes. And also this can be taken from genes. Genes change by random changes, but species as a whole can be changes which are deterministic. So, Temo, please. I mean, could there be a way of reconciling your way of looking at evolution and this rule-based evolution? Can you have order on the large scale, order in the large, even indeterminism and randomness in the small?
Although I'm a probabilist, so I would think that every deterministic system is just a special case of a probabilistic system. I don't know if physicists find this offending or not, but I think the correct way to do it is just to handle it in a probabilistic sense. And if you learn that there is something that happens with probability 1, then you just learn this as an outcome of your analysis. But you should not sort of take deterministic models as a starting point. And in fact, this friend that Eric mentioned, when they are doing their reconstruction in this field of linguistics where everything is supposed to be deterministic, they do use probabilistic models. And he has told me actually that he has problems publishing this because the referees say, well, okay, here's just another guy trying to use this probabilistic stuff, but we've already agreed that this is rubbish. But that's the only way he can make it work in practice, because there are instances in the data that you cannot explain by, well, if you insist on deterministic rule, it becomes extremely complicated, because it has to list every word basically on its own and create a rule for every individual word that doesn't match the general rule. So it's much more simple to just say that, well, there is a tendency for, say, an A to become an E in this context. But then there are exceptions. There are these random counterexamples that sometimes happen. And I don't know, maybe that is useful or not for many other systems, including universe or climate and stuff like that. But I would, that's my way. I sort of try to think about things that way.
It seems, so we were talking last night, in paleontology, this approach you discussed last night is used. And it's completely thought of in this way, and there's no underlying equation of motion, but we have data. We have data in the past, we have data in the present, and it's what I would call, put in the class for thinking, in some sense, a system without any equations of motion. However, we have climate on the same time scales, which we do all think has some equations of motion. We hope, right? I mean, we so much, yeah, we could talk about that later. But in principle, we think, we know the carbon cycle, we know how the atmosphere and the ocean flow and so forth. And so here we have systems that live on the same time scale, thought of in a different way. Is it useful to have a comparison where you test the idea of, because my opinion actually is that, right, that species do things because the climate changes. Right? They do that. Question is, on what time scale is that relevant for the evolution of species, mutations, and so forth? Seems that there might be a reasonable way to think about doing a comparison principle.
Because there's the issue of autonomous and non-autonomous. I was trying to make a separation between things, and just to simplify the discussion, probably at the end we find one problem we can deal with, and all the rest is hopeless. Because if it's non-autonomous, as you just say, if there are extra ingredients that are not in the data, right? I mean, that are not You know, for example, if there is another universe who is influencing this universe, and we don't know this, wormholes are going through, etc.
What about Hashem?
Hashem. Then there's no way, right? I mean, then there's no way that you can reconstruct, because you assume that it's autonomous from the very start, right, in order to be able to proceed. Now, there are many problems not autonomous, right? I mean, you take, I don't know, take living organisms, they're not autonomous, they're different on Sunday and Monday. And even though you put them under the same conditions, they're going to do entirely different things. I mean,
The genes are the same.
yeah, but the mood is different, right?
That's
You
true.
wake up on Sunday, you're upset with the world, you do different things. Then waking up on Monday where you were for some reason happy, and you know,
But the
then the
genes are
whole
not
day is
same.
different, even though you go to the same work, you're doing the same things, but you know, so how do you put this into analysis? It's quite hopeless, right? And I'm sure that many of these are of that type, and then scratch them off.
But I suppose as long as you can identify a quantity, like, you know, for in that example, like maximization of happiness, you know, then you have something. You know,
Not everybody wants to maximize the happiness. Some other people want to maximize some want to maximize the death. Alcohol, for example.
But maybe for them it's a
The same thing.
It's the same thing. It's the same thing, as long as there is a quantity that is, you know, that's...
But aren't these dichotomies really useful? Because if we're saying that this is
It's
a
not
closed system,
dichotomy,
this is an open system,
It's not economy, it's much more, it's multicotomy. I think one has to begin to look at all these systems and separate them into classes. What?
but aren't they always like continuums?
Sorry?
They're continuums. The genes, they sort of appear to be autonomous to some extent, but there are features that are sort of affecting them from outside. I wouldn't say that this makes the problem hopeless. Obviously, there's been great changes in evolutionary reconstruction. The texts, I think it's even more difficult. It's clear that there are outside factors affecting the way the texts evolve, and we should take that into account, but I would still say it's hopeless. And I think everything else here, except the universe, because I suppose that's by definition autonomous, that it includes everything. So by definition, everything else but the universe is a system that is sort of affected by outside stuff that we
There are
exclude.
a huge amount of
Even
answers
with the universe,
solving the universe.
yeah, even with the universe, when we say the universe is not the whole universe, it's just a part of it.
Which is influenced by the rest. Yeah.
Yes,
Right.
exactly, but as long as, you know, the rest, like, in this case, if just all around it is homogeneous and things, then...
So we can argue on which it goes out of the...
Completely hopeless. It's sort of more or less hopeless, depending on the case.
Yeah,
It depends on your optimism.
Yeah,
you never have really...
And you seem to be an optimist.
I guess.
So I believe that, you know, one of the basic principles of linguistics is that language change and language, the meaning is, the sounds in the language are independent of the meaning and not influenced by anything. That's the principle of Saussure. So, as you know.
If you start by the Strauss, then this is
Okay, so then we have two different giants with different opinions. Uriel, final words. We have to end quite sharp. I think nobody is really convinced that these reconstruction problems have anything to do with one another except maybe you, as an optimist.
But I think I also...
Okay.
Another optimist.
This is a bad discussion, everyone agrees.
No, Itamar doesn't, and I don't. And I'm not sure about Robert.
But I think there are classes.
Yeah.
And one has to separate,
You cannot
right?
think that all classes will merge in unified approach.
Uriel, you have a
No,
challenge
there is,
now.
I
Convince us we are wrong.
think there are certain things that are common to all of it. Namely, that frequently we have to think in terms of two-point boundary problems where the information at the two ends may be of very different nature. But in doing reconstruction of deterministic or random things, it is useful to take into account all the constraints and try to do it by whenever possible, by a variational method, including variations on probabilities.
Okay. Any final words, Roberto? Yeah, okay. What is physics?
Let me say a few words about
Yes,
physics.
Grisha,
If
finally.
you do anything, then you'll be sure that physics is doing better. And that's because our problems are simply essentially. So, not all that there are too much stuff here, but simply speaking, what most telling yesterday, this problem like this. You have a present state, you want to know what left to it, but there is an internal randomness in it. It has a kind of maybe dynamic part, but it contains randomness. So what you do, you find the most probable path to this point. There are a class of problems like this. You ask if physicists do it, of course, and of course, as everything physicists do it best of all. That's the way we call method of optimal fluctuation, saddle point integration of path integral, or whatever. That means we are looking for extremum of probability, and of course, the mathematician also do it. So in a sense, it's a very well-defined subject how we do it and how technically we work on it. I'll give a particular example tomorrow at my talk. And in this respect, there are many important and interesting lessons that one can learn looking how physicists do it, because you really want to find this path, you want this maximum to be sharp. Well, first of all, as Uriel said, you need to be convex, okay? In all directions. Then you look at it, and being there is so multi-parametrical space, it's not convex in all dimensions. It tells you that you need to take into account some direction, some parameters, some variables, in not this simple saddle point integration view. What will be then after it, the so-called renormalized action. And I agree with Uriel that the question of motion is not necessarily important. You need weight function. It could be something which you build out of path integral. It could be something that you have from other. You need weight function. You need to tell you what is the probability of any given path. And you look for sharp. And when you look for sharp, it's a non-trivial game in a multidimensional space. Some things you need to account, taking into account that the evolution of languages goes this way on average, and then randomness. And it's kind of, I mean, there are two methods of theoretical physics. Perturbation theory and saddle point analysis. So approximately half of the physicists of theoretic, yeah, there are no other methods. If you have ever thought that there are more methods, no, there are two. There are two modes, multiple rewriting and steering. There are two methods. There is perturbation theory and saddle point.
There are systems where you have a lot of sharp maxima. So when you do the saddle point, you have to make a saddle point on something that is unclear.
In the glass we have many maxima, and you look for global maximum.
Yeah,
that's another modification which I guess people in other discipline did not have their nightmare that we have here. We also forced here. But in a sense, I mean, it's kind of, I mean, you know, it's like prose. It's something you only speak it all the time. I mean, of course, I mean, we do this reconstruction all the time. And condensed matter, particularly, is a field which is built on you know, on finding these optimal fluctuations, which are basically finding an experiment of probability.
So I think we should paraphrase the famous statement of Niels Bohr that you cannot make, that it's very difficult to make postdictions, especially about the past.
Okay,